Okay, can you hear me now? Ah, cool. I'm so sorry about that. I thought I had sorted the software problem, but apparently not. Fast. Didn't say that. Ah, cool. Good. So let's say we have A is converted into B with a rate constant of K1, and B is then consumed with a rate constant K2. Okay? As I said, I'm very sorry about that problem. Okay, now we can write what happens to A. Okay, so we have dA over dt equals, what do I write? What do I have to write? Plus or minus? Oh, okay. Here's a question from Panda Gaming. dA just simply means change in the concentration of A, and dt just simply means a very small time interval. Okay, we have minus, so we write minus k times A to the power of m. We just had that, so that's nothing terribly interesting. Now we write dB over dt, so we look at it from B's perspective. And for a moment, let's just simply ignore this part here, this K2. Just simply let's ignore that for the time being. So dB over dt, we said that earlier, would be plus K1 times A to the power of m, right? So that's what happens in this region here. And yet we have another component which is then now this bit here. So here we would write minus K2 times B to the power of, let's say, n. Okay? So in this case, the rate for B is actually composed of two components, as we see here. The first component is the production of B, and the second component is the consumption of B. So here that is the production, and that one here is the consumption. Okay? Now, what do we get if production is the same as the consumption? We get 0. Ooh! Because obviously production and consumption cancel each other out. What does that actually mean? dB, Alana is right, dB over dt equals 0. What does that mean in plain English? How would you interpret that? What do you think? B is being used, yes, there's no change in B over time. And here, Daniela puts it absolutely right. This situation where the production and the consumption cancel each other out is called a steady state. A steady state What does that mean actually for the concentration of B? Alex is right, it's some kind of equilibrium, but we are coming to the case of an equilibrium in a moment. And the question is, what happens to B? B stays constant. Is B zero? Is the concentration of B zero? No, the concentration of B can be anything. It only means that there is no further change in the concentration of B. But the concentration of B can be whatever you get from it. Now, Alex just mentioned a word, and I want to come back to that in a moment. Okay, we should be back in business. Am I back? Yes, good. Are we back? Back. Thank you. I'm sorry about that. I don't know. It's probably the university network. And tell you what, next time I stay at home and try it from home. Ha! Gucci, yeah. So K1, B, and now instead of consuming B in that direction, as we had, what we do is we get B to convert into A again. And I write that with K minus 1, subscript minus 1, I should say. So what's happening here? We can write dA over dt equals. Let's look at the K1 reaction. So dA over dt equals, and you tell me what I have to write. You tell me what I have to write for dA over dt. Yep, you're right, Danica. Minus K1 times A to the power of M. And now we also get the reverse reaction. So in this case, we get plus K minus 1 times B to the power of N. Amy, absolutely spot on. Yes. And for B, dB is a similar situation, equals minus K minus 1 B to the power of N plus K1 A to the power of M. Does that make sense? What happens if, again, our consumption is the same as the production? What happens if production is the same as the consumption? 0. The rate is 0. And here, the reuse says it's a steady state. It is actually a special form of a steady state, because this steady state applies to both. It applies to A and it applies to B. And because it applies to both of them, this is called the equilibrium. We have reached an equilibrium. What does that mean? And you are right, please, the rate is 0, nothing changes anymore. We have fixed concentration of A and B. Now let's explore that for a moment a little bit further. Hopefully I'm back. This really gets on my nerves. I think I need to do something about the university network. Back again, thank you. dA minus K1 times A to the power of M plus K minus 1 times B to the power of N. And if they are both the same, we have 0 equals minus K1 times A to the power of M plus K minus 1 times B to the power of N. Or I can Panda, I think you are absolutely right. I need to find a way how I can do that better with a hardwired connection. So we can actually solve this. We bring just simply this term to the other side and we get K1 A to the power of M equals K minus 1 times B to the power of N. Yeah, guys, you are right. It's just the thing with the Ethernet cable is not that simple when you work with an iPad. Is it blurry for anyone else? Oh, because here on my computer it's quite good actually. Ah. Try refreshing. Yeah, that's a good idea. Crystal clear. Ah. Weird. Very weird. Anyway, let me just quickly get on with that. And what we can do is now we bring all the concentrations to one side and all the rate constants to the other side. And what we get is K1 over K minus 1 equals B to the power of N divided by A to the power of M. Oh, Ethan, that's a very good question. If we have that reaction A to B and back, so K1 for example, for A, when we look at from A, we look at the consumption of A, but the production of B. So consumption means minus K1, production means plus K1. Does that make sense to you, Ethan? Brilliant. Now we have this sort of equation here. Have you ever seen something like that? Because here it comes. If we look at this one here. Yes, please, you have. You have. Okay, I'm trying a new page. Keep your fingers crossed. New page, okay? Are we back? I'm getting closer to this problem. The more crushes I have, the more I learn about it. So if we have I give up. I honestly give up. A to the power of m, no, sorry, b to the power of m divided by a to the power of n equals k, what was it, k1 over k minus 1. That is what we had on the previous screen. Yeah? This thing here is combined. And it is called usually K ec. It's the equilibrium constant. This is actually the definition of the equilibrium constant. Yeah, b to the power of n, I just changed it. My memory is so short I can't even remember what I did on the previous screen. So the definition of the equilibrium constant is nothing but a combination of two rate constants. And how does that actually relate to life, universe, and everything? Well, obviously, the enzymes, where we've seen that the rate that, I come back to that, Irene. In enzymes, the kinetics plays a role because the rate order shifts from 0 to 1 depending on the substrate concentration. Equilibrium, things reach, if you like, a special state of, or case of steady state, and the equilibrium constant is given by the ratio of the rate constants. Likewise, for a steady state, and in our organism, everything is really based on steady state. But in the case of N and M, does it tell us how many moles there are in the reaction? No. Irene, that's an excellent question. Let's revise that quickly. The rate order tells us actually a mathematical concept. The molecularity of a reaction tells us how many moles of something actually participate in this reaction. So the rate order, the N's and M's, don't tell us anything about how many molecules or atoms are reacting. So it's very good that you asked this question. So I just want to quickly show you some consequences of the whole thing. And we said we could look at A, B like that, where actually we have a sort of a toy pathway, and we can have B as an inhibitor of the reaction. Now, what does that mean? Excuse me. What does that mean? If A is produced, then it is consumed. B is produced. B then inhibits the production of A. If no more A is produced, then no more B is produced. B is consumed. If no more B is produced, then A is uninhibited. And more A is produced, which produces more B. B inhibits, less A is produced. So in a way, it's the mind boggles. So how can we visualize that? Let me see if I find a picture for that. Here is a picture exactly for this case. So here on the x-axis we have time. And here we have the concentration of A or B. And when we follow the time, what we see that in a case of a negative feedback loop, we see some kind of slight oscillation first. That's the red one is A, the blue one is B. But then everything reaches the steady state condition and becomes stable. So a negative feedback loop stabilizes a system. We reach homeostasis. And that is extremely important, because otherwise we would always have an enormous amount of fluctuations. So, negative feedback is associated with stabilizing our life, basically. Life would not exist without these negative feedback loops. What about, and this time I'm smarter, I just simply, no, I'm not smarter. Okay. What about we have a case like that? Here we have a positive feedback loop, and B activates A. What happens in this case? Now something really, really bizarre happens, and we discussed that the other day, and this is the picture of what happens in this case. Here on the x-axis we plot A and here we have B. And what we end up with is a bizarre situation. Here we have the situation for A and B if A and B are small. So if A and B are small, we have low concentrations of A and B. But if the concentrations of A and B get higher, we get a stable state with A and B high. So we can have actually not one stable state, we can have two stable states in a positive feedback loop. So positive feedback. And that is something absolutely fascinating. Positive feedback loop allows for two stable steady-state positions. A negative feedback loop results in one steady-state position. And now here it comes. Something really, really fascinating. Are you ready for that? It probably crashes again. What happens if we have a complex system? Are we back? Are we back? Just one more minute, please, because I want to show you something really, really cool. What happens if we have a system of several feedback loops? Inhibition, inhibition, and this one inhibits as well. What is your prediction? What will happen in this case? Will we get a stable, steady state? What do you think? Will we get a stable, steady state? What's your gut instinct? Alana says yes, yes, yes. Anyone else? Amy puts a question mark behind it. Shall I tell you what happens? You're all right and wrong. Ha! You didn't expect that. This is actually what happens. The system starts to oscillate. So for example, if you look at A, here, the concentration, and you have time here, the concentration of A goes up, goes down, up, down. And B does exactly the same, and C does exactly the same. We have an oscillating system. You would never have predicted that just simply from these feedback loops, would you? And this is what actually is called emergence. Emergence indicates that we get new properties by combining simple elements with each other. We get an oscillating system by just simply putting 3 feedback loops together. If you have 1 feedback loop, you stabilize the system. If you have 2 feedback loops, 2 negative feedback loops, you again get a bistable system. If you put 3 feedback loops together, you get an oscillating system. So there is a lot going on, and you can you think of a system where an oscillation is evident in life? Where would you see oscillations? Where would you see oscillations? Homeostasis? In homeostasis, it's trying to stabilize it. But true oscillations, pregnancies, specify? I'm not entirely sure. On a seismograph here, brainwaves. Brainwaves is great. Hormonal oscillations, yes, absolutely right. Sleep pattern. At night, you want to go to sleep? Well, I do. My student days are over. At night, melatonin is produced, which sends you to sleep. During the day, you wake up. In the cell cycle, you have cyclic events. You go through different phases and they come back again. Meiosis, mitosis, S phase, G1, G2 phases, they are all regulated by these cyclic events and by feedback loops that inhibit each other. So I think that is something that I find incredibly fascinating, and maybe I will do a few more videos on that. So for now, the time is up. I apologize for the frequent crashes, and I'll try to sort them out. And well, thank you very much for watching. I hope you enjoyed it. Take care and see you soon. Bye bye.